All right, we're going to go over the exam. Exam 4. We've got question 1. A spontaneous reaction occurs, like it says, simplest one here, without ongoing outside intervention. So we just have this reaction or the reactants there or whatever. Spontaneous reaction should just occur by itself. We shouldn't have to add anything to it. What would be the sign? Go into this. What would the sign be for delta S system and delta S surroundings? All right, so we've got our reaction looks like this. MgCO3, and that's a solid. And that goes to MgCO, or sorry, MgO, which is a solid, and CO2, which is a gas. For delta S system, we can at least figure out the sign on this. What should the sign for this reaction be? Should we see positive sign or negative sign? Is the entropy increasing or decreasing? Well, I'm going from 1 molecule to 2, so delta S is probably increasing, and I'm going from a solid to a solid and a gas. So also based on the phase, we should have a positive delta S system here. Delta S surroundings is equal to negative delta H system over T. And in this case, we're given the delta H for the system. It's positive 123 kilojoules. So I know with the negative sign out in front, our delta S surroundings should be something negative. So our answer here should be positive for the delta S system, negative for delta S surroundings. Okay, identify the process in which entropy, where did it go? There we go. Identify the process in which the entropy increases or decreases, sorry. Increase in the number of moles of gas during a chemical reaction. That should be an increase in entropy. Transitioning from a solid to a gas, that's going from a more ordered state to less, so that should be an increase. Transitioning from a liquid to a gas, same thing, going from a more ordered state to less. But B, the phase transition from a gas to a liquid should be going from a less ordered state to a more ordered state. So in that case, we would see the entropy decreasing only for B. All right. Identify or given the values. So we have delta H here is equal to negative 75 kilojoules. Delta S system is equal to negative 127 joules per Kelvin. And we want to know above what temperature would this reaction suddenly become non-spontaneous. So our delta G, in that case, we want some delta G that's positive, is going to give us a non-spontaneous reaction. So right before that happens, delta G would be equal to 0, and then any value greater than that will give us a positive delta G. Our delta G equation is delta H minus T delta S, and we have actual values here for that. So I'm going to set delta G equal to 0. You'll notice the units for delta H are kilojoules, the units for delta S are joules. So I'm going to convert my delta H into joules as well. So the units agree. You could go the other way if you want. And you could do convert your delta S from joules to kilojoules and leave your delta H in kilojoules. Either will work. So I've got my equation here. Add 75,000 joules to both sides, and I get this. Divide both sides by that 127. Oop. And negative t equals negative 590.6, or t equals 590.6 Kelvin. So once we go above that temperature, we will suddenly become non-spontaneous. Place the following in order of increasing molar entropy. I've got H2 and O2 and F2. So all of these are diatomic gases, so they're similar in that regard. The difference between them is going to be their mass. This is going to have a mass of around 2, this 32, and I believe this around 38. So as the atomic mass increases, the entropy should increase. So if we're going in increasing order, this should look like that. 6, calculate delta S for the following reaction. We have C2H2 plus H2 goes to give us C2H4. We're given all the individual entropies of formation of these. So the C2H2 is 200.9, H2 130.7, C2H4 is 219.3, and I'm just going to do the product summation again of the products minus the reactants. And in this case, all the coefficients are 1. So I'd have 1 times 219.3, and that's my products minus my reactants, C2, H2 times 1 plus my H2 130.7, and there's only one of those. So what I get is negative 112 or 112.3. 8, which of the following is not true for delta G? There we go. So if delta G is greater than 0, the reaction is spontaneous in the forward reaction. No. If, as written, if the reaction is spontaneous, we should have a delta G that's negative, so it should be less than 0. That's not true. If Q is equal to 1, then delta G non-standard is equal to delta G standard. Based on that reaction equation, if you remember, we've got RT times the ln of Q, and that'd be 0, so this would be true. If delta G reaction is less than 0, the reaction is spontaneous in the forward direction. Yes, delta G is negative. That means we have a spontaneous reaction. And under equilibrium concentrations, delta G reaction non-standard should be 0. Correct, it would not be favored in the forward or reverse direction at equilibrium. So that's why it would be A in that instance. Calculate delta G for the following reaction. So we've got calcium carbonate, and that's a solid, and that decomposes into calcium oxide, which is a solid, and CO2, which is a gas. And the delta G standard for this is positive 131.1 kilojoules. Our pressure for CO2 is 0.033 atmospheres. So if you look at your equations, we've got a non-standard pressure, and we have our standard delta G. So what we want to find is our delta G non-standard, and that's equal to delta G standard plus R times T times the ln of Q. Q is going to be products over reactants, but the only product we have that isn't a gas, or isn't a solid, is CO2. So Q is just going to be equal to 0.033 atmospheres over 1 right there. Delta G is in kilojoules, but my R is in joules. So what I'm going to do is convert delta G into joules. And then I've got my R, my ideal gas constant, times my temperature. Yep, they said at 298. And then times the ln of 0.033. And what I should have here is 131,100 joules minus 8,452. And we get positive 122,648 joules, or I think the answer here is in kilojoules. So 122.6 or 123 kilojoules right there. Determine the equilibrium constant for the following reaction at 655 degrees. You could either use delta H and delta S to find delta G. So you could do this and do delta H minus T delta S and use your delta H value, your delta S value, and your temperature at 655 to find delta G. And then just plug in for this equation here. Or you could utilize this equation and you've got negative delta vaporization, or sorry, enthalpy for the reaction over R. So I'd have 158,000 over R times 1 over T plus my delta S over R. Either one will work. And then take E here to cancel that out. Yep. And you get K being equal to like 12.99, somewhere around there. And again, this is the equilibrium constant you're finding, not the energy. So it's unitless. Your joules here would cancel joules, mole, Kelvin, and then your temperatures would cancel there. Yeah. So what elements being reduced in the following reaction? So I've got this permanganate ion plus H2 C2O4, and that goes to give me Mn2 plus and CO2. Each oxygen here is -2, which makes the manganese +7. Hydrogen's first on the table. Next is oxygen. So I've got +2 -8, so +6 is left. So each carbon here should be +3. The manganese here is +2, and now these are -2s, and here the carbon should be +4. So the carbon went from a 3 to 4 and was oxidized, but the manganese went from a 7 to a 2. It became less positive, and therefore was reduced. balance the following reaction as it occurs in basic solution. All right. NO2 minus plus aluminum goes to NH3 plus aluminum oxide. All right. And so we've got minus 2s on my oxygens again, plus 3 on the nitrogen, 0 on that aluminum, plus 1s on the hydrogens here. So now the nitrogen's a minus 3, minus 2 on my oxygens, and plus 3 on my aluminum. So nitrogen in this case is reduced. So we can start with that, doesn't matter, or we could start with the oxidation. But we're going to go from a plus 3 to a minus 3. So we got to add 6 electrons to that. And then over here, we have our NH3. Now I have 2 oxygens on the left that I don't have on the right. So I'm going to add 2 waters there. And then I've got 7 hydrogens now on the right that aren't on the left. So I'm going to add 7 hydrogens. And because it's in basic solution, I'm going to add 7 hydroxides to neutralize that. And since I can't create matter, if I added 7 OHs to the left, I'm going to add 7 to the right. I can take these 7 H pluses and OH minuses, and I can turn those into 7 waters. So that should balance 14. 1, 2, 3, it's 14 there. Yep, that looks good. So that one's done at the moment. And then we'll go to the aluminum. So we're going from aluminum 0 to aluminum 3. So we've got to lose 3 electrons. And I've got 2 oxygens on the right that aren't accounted for. So I'm going to add 2 waters to that end. And then I've got 4 hydrogens that aren't accounted for. So I'm going to add those in. Then add my 4 OHs because it's basic and I want to neutralize that. There we go. Then again, we can take these 4, oh, actually, before I even, well, yeah, we'll do that. These 4 H's and these 4 OHs I can turn into 4 H2O. Now, I think I'm balanced. I can add them together, 8 and 8, yep. But the electrons don't match. I have 6 electrons on the top and 3 on the bottom. So I need to multiply the whole thing through on the bottom by 2. So I'm going to go 2 aluminums, 4 H2Os, 8 OHs. Ooh, dang it. 2 of these. That changes to 6. And this should change to 8. Now I can add them and cancel anything that is the same. So we'll start with, there we go, my 6 electrons. These 2 waters are going to cancel 2 of those. These 7 waters are going to cancel 7 of those. These 7 OHs are going to cancel 7 of those. So let's see if we add that at the moment anyway. What does that look like? Come on. If I get 2. Two Al plus NO2 plus 2H2O plus OH minus and then technically one of these waters, since we have 2 waters on the left and one on the right, I could get rid of that one, but we're just concerned with the coefficients now in front of the OH which is a 1, and the coefficient in front of aluminum, which is a 2. We've got a mixture of sodium, bromide, and KCl. So I've got two possible reductions. One is the reduction of sodium to sodium metal, and the other is the reduction of potassium to potassium metal. And if I go to so one of these reductions is going to occur preferentially over the other. If I go to my constants in the back, I see this is negative 2.71 volts. This is negative 2.92. Yep. So the reduction is going to be the one that is higher on the table. As we go up on the table of standard reduction potentials, their reductions are more likely to occur. And in that case, this is this one. It's a negative value, but it's higher on the table. It's less negative than the potassium. So preferentially, we should see the reduction of the sodium. If we do the other one for my oxidations, we're going to have the oxidation of Br minus forming Br2. And the other oxidation is going to be the chloride, 2Cl minus, oxidizing, each one of those losing an electron. Oops, should be a 2 in front of that, and a 2 in front of that. And for these, our oxidation potentials are plus 109 and plus 1.36. Oxidation preferably occurs from lower on the table. So if we have two standard reaction potentials, the one that's lower is the one that's probably going to be oxidized. So these are both positive, but if we look at the values, this is the one that would be lower on the table. And so bromide is what we should see being oxidized between the two possible oxidations. Okay, so now we've got copper. We're looking at the reduction, and it's copper 2 plus being reduced to copper solid. And we want to deplate it, and we're told the amps and the length of time, 30 minutes that it's going to go. So we're going to do our conversion. We're going to start with 30 minutes, and we want to get to seconds because amps are coulombs per second. Then we can multiply by our amps to cancel out our seconds. Then we're going to cancel out our coulombs by dividing by Faraday's constant. And then when we look at the reaction, we need to go from moles of electrons to moles of copper. Well, copper 2 plus going to 0. Each one of those is gaining 2 electrons. So we've got 1 mole of copper for every 2 moles of electrons. And then the very last thing we do is we would multiply by the molar mass of copper, and that is 63.546. So if we go through this, if we set it up properly, minutes cancel, seconds cancel, coulombs cancel, moles of electrons cancel, moles of copper cancel, and we're left with the units that we want, which are grams. And if I plug all this in, 30 times 60 times 6 divided by 96,485 divided by 2 times 63.546 gives me 3.556, or your answer choice 3.56. There it is, yeah. 3.56 grams. From the cell notation for the following redox reaction. So I've got 2ClO2 plus 2I minus, and that goes to 2ClO2 minus and an I2. Oxygen's here minus 2, chlorine is plus 4, we need to identify what is being oxidized and what is being reduced so we can figure out what side is our anode and what side is our cathode. A monoatomic ion, whatever its charge is its oxidation state. Now, instead of the two oxygens, -4 having to add up to 0 like they did over here, they'd add up to -1. Oxidation state on our chlorine then would be +3. And here's an element, it's an naturally occurring state, so it should be 0. So I can see in this case the chlorine gained an electron. So it was reduced, and the iodines each lost an electron. So it was oxidized. So then oxidation happens on the anode. That's the iodine. The iodine, though, is not a metal. It is not conductive. So I want to pick some kind of electrode that is conductive for my anode. Then we're going to have our phase barrier to what's actually in that electrolytic solution. And that's going to be my aqueous I- ions. And then I've got a phase to the I2, which I think was a solid. Then we've got our salt barrier going to the other half of the reaction, the cathode again, where the reduction occurs. And there I've got what's contained in that beaker. So we've got that gas. Phase barrier then to the aqueous component, or vice versa. Could be the aqueous part first, then the gas. This is also not a solid, not conductive. So in terms of the actual cathode, the electrode there, again, we would pick something conductive like platinum. So this should be your cell notation for that particular redox reaction. Standard EMF for a cell. So now we've got standard EMF, E cell, standard is plus 0.48 volts. We have our reaction. We have our concentrations. As the reaction's written, we have solid zinc. We have the aqueous nickel ion. I've got then the zinc being oxidized to its aqueous form and the nickel being reduced to the solid metal, the 0 form. So we're going to use the equation, the Nernst equation, E cell equals E cell standard minus 0.0592 over N times the log of Q. Q is going to be the zinc 2 plus concentration, because that's our products over reactants, in this case the nickel 2 plus. So I've got E cell standard 0.48 volts minus. N should be 2, the number of electrons being transferred from the nickel and the zinc. Zinc's going from 0 to +2, so it's losing 2. Nickel's going from +2 to 0, so it's gaining 2. So I'd have 0.0592 divided by 2, which is going to give me 0.0296. And then the log of in this case, where did it go? 0.01 over 3.5, the two concentrations that were given there. What we should have is 0.48 minus a negative 0.0753. So 0.48 plus that, we get 0.555. 0.5, or out of the options, if you round, 0.56 volts. What would be the standard potential for the following? So again, we write that out. We got tin 0 plus the 2 silver plus, and then we go to tin 2 plus and silver 0. This is 0 plus 1 plus 2, 0. So again, this is oxidized. This is reduced, making this the cathode, and this the anode, and we're just going to do cathode minus anode. If we go to our table, for values there, we can see the standard reduction potentials. For silver, for the cathode, it is 0.80 volts, and for the tin, it is negative 0.14 volts. So what we should get is a positive 0.94 volts for 16. 17, lead 192 is most likely to decay via what route, what type of decay? So lead is 82, we have lead 192, subtract 82 from 192, and what we have is 110 proton or neutrons, and we have 82 protons. If we do our N to Z ratio, what we can see is that is equal to 1.34, but we're on the heavier end of the elements, that 40 to 80-ish range. So we want this to be closer to 1.5. So this is too small. So I want to increase that ratio. And to do that, excuse me, ideally, I would make the top number larger and I would make the bottom number smaller. If I could, I would go from 110 neutrons to 111 neutrons, and I would go from 82 protons to 81 protons. And the thing that will do that is positron emission. To kick out the positive charge in the proton, turning it into a neutron. So the top number goes up by 1, the bottom number goes down by 1, and if we do this, we should see our ratio increase, and we should be closer, at least, to that 1.5. What's the daughter nuclide for the following reaction? So I've got 104, 47, and that's silver. And we were looking at this reaction right here. It looks like it kicked out a beta particle. And so what we're trying to find out is this. For silver, should be 57 neutrons and 47 protons. When we get beta emission, what happens is a neutron converts into a proton. So neutron should go down by 1. Proton should go up by 1. And in this case, 56 plus 48 is the same thing as 57 plus 47. So that would be 104. But now our atomic number is 48. And if we go to the periodic table, what we see for 48 should be cadmium. And in fact, it is. Based on the missing particle here. All right, so we got thorium 229. And we are here at 225.88 for radium. So I can see right here, we lost something with a mass number of 4 and 2 protons. And the thing that has a mass number of 4, 2 protons, 2 neutrons total is an alpha particle. So this would have to be alpha decay then, if it lost an alpha particle. And lastly, describe what occurs during beta emission. Beta decay, again, is where a neutron loses a negatively charged particle and turns into a proton. So we should see the atomic number increasing because the neutrons go up by or down by one, but the protons go up by one. The mass number should be unchanged. So that's why the answer there should be B. That's it. Again, if you think there's an issue with your Scantron, your score doesn't match in web courses as to what you thought it would be, stop by any of my office hours. Monday 1 to 2, Tuesday 10 to 11, Wednesday 10 to 11, Thursday 1 to 2, Friday 10 to 11. I'll gladly pull the Scantron and see if it matches. If it doesn't match, if I can see, you erased an answer and you clearly bubbled in D and it just couldn't tell if you had marked B or D, but I can see you marked D and D is the correct answer. We'll change your score on there to reflect that. Otherwise, we'll see you Monday.